Hello and welcome to SAE Tomorrow Today. I am your host, Grayson Brulte. On today's episode, we're absolutely honored to have Kyle Schmidt, Vice President, New Product Development and R&T Engineering, Safran Landing Systems. On today's episode, Kyle and I discussed lightweight landing gear and the decarbonization of aviation. We hope you enjoy this episode. Kyle, welcome to the podcast.
Thanks, Grayson. It's great to be here.
I'm super excited to have you here because I think landing gear is cool. You think landing gear is cool. And I was speaking to my wife and I said the most important part, without really high quality landing gear, the plane can't take off and can't come down. So I'm really looking forward to this conversation. To kick things off, what goes into landing gear?
Landing gear is a really multidisciplinary topic. You've got structural kind of engineering. It's really what I love about landing gear is it's basically a robot that moves from one position to another. It absorbs energy, but it's also the main structural item that's holding up the airplane on the ground. So it's got to be reliable. It's got to work every time. And so there's a lot that goes into it to make sure that it's strong enough. It's going to last the life. It's going to be light, because nobody wants the landing gear when you're flying, right? Because then it's just unwanted baggage, and it just goes to fuel burn and everything. So you really only want it, when you're taking off and landing, as you said, and when you're rolling around on the ground. So we put a lot of effort into making sure that they're lightweight, that they're strong, that they're going to last a long time, the 30 years of an airplane's life.
Landing gear lasts 30 years?
Yeah, they usually have an overhaul or two in that sort of period, but most large commercial airplanes are designed usually for something around a 30-year life. Some can last longer than that, but that's kind of the nominal value that's taken. And landing gear designed to last that these days, often with only one shop visit where they're taken off the airplane, pulled apart, stripped down, inspected, and then rebuilt back up and put back in service.
You think about it, these planes weigh 100-ton plus planes. They're landing and taking off multiple times a day. They're landing on different types of surfaces. How is the landing gear engineer to take that abuse and that impact that they do every day? Yeah,
so a lot of work goes into figuring out, what is the likely service experience that an airplane is going to see? What's the spectrum of loads that are going to be experienced? The landing gear and the rest of the aircraft structure are designed to take the static strength of an event that may only ever happen once in the lifetime of the airplane, or maybe not in the life of every individual airplane. But then from a day-to-day basis, we're worried about the fatigue strength, we're worried about the endurance. And so what are the loads that an airplane sees, day to day? We put those with experience. We build up overall the outline, the spectrum of how things are experienced, and then we design for that. We look at a lot of analysis to make sure that the metal parts are going to withstand that over time. We do a lot of testing to verify that, and when we do a lot of follow-up in service to make sure that the assumptions we've made as a company, as an industry, are correct, and that the airplanes are actually being used that way.
I'll ask you a scenario. For instance, on this one side, we have a cargo airplane, and on this side, we have a passenger commercial plane. Obviously, the weights are different. The cargo plane could be doing more. Do you have to engineer the landing gear different based on the weight of what the plane's going to be hauling, say cargo versus passenger?
Well, it really depends. If it's a purpose-built cargo airplane, like some sort of military transport airplane, then it really would be designed a little bit differently. The mission would be different right from the outset, and things would go into it to consider that there's really quite a difference in the behavior. And often a lot of military transport aircraft are designed to operate to semi-improved runways. They're going to have rougher runways, soft fields, things like that. A lot of commercial cargo is done in modified passenger aircraft. So it's usually a passenger airplane that's been designed from the outset to carry containers in the belly underneath the floor, and then it's been adapted to perhaps take containers on the floor. And those, when they make those adaptations at an aircraft level, they're generally working within what was originally intended for the passenger airplane. So the missions aren't overly different. So it really depends on what the outset is from the beginning.
When a plane's coming in for landing, let's just use a tarmac that you would see around the world, commercial airport. Is there a maximum speed that the plane should come in for the impact on the brakes?
There's not necessarily a maximum there. That depends on the type of airplane that it is. Generally, you want to get the airplane moving as slowly as you can, safely, before you come into the touchdown. It reduces the amount of energy you need to put into the brakes. It reduces the amount of damage that's done to the tire as the tire is spun up to speed. I guess there are some theoretical limits. You probably couldn't land at Mach 1. It would probably really drive some issues into the airplane. But often, because you need to spin up the tires, a high-speed landing is particularly hard on the tires. The space shuttle, which landed at quite a high speed, that was quite demanding on the tires because it when those tires go from 0 to 300 miles per hour in an instant.
There was about a couple weeks ago, there was a gentleman, he was calling like a football match as the plane's in Heathrow, the wind's coming from the left, it's coming from the right. I found it engaging. I'm like, I'm watching a football match. What impact does that have on the landing gear? Those planes are wobbling left or right. Oh, this one's it's going down. It's turned. Oh, the pilot's coming back, and he's doing this thing. What impact does that have in those windy conditions?
I mean, really, it's probably very exciting to watch. I think I've watched some of that as well. So there's a couple airports, especially in the UK, where there's spotters get out there, and there's a lot of good wind, and they're all over the sky, and they come down and touch down, and it looks incredibly. It's riveting to watch this, and it's quite a spectacle. I think in the landing gear world, you could actually, from the landing gear's point of view, it's all pretty boring, I would imagine. Really, the landing gear is designed to take that sort of abuse. Anything which is inside the normal envelope of operation really isn't going to cause too much of a problem. And so, when you look at an airplane, most large commercial airplanes, by regulation, are designed to be able to hit the ground at 10 feet per second as the vertical speed that they're coming down at. And there's usually a bit of margin to go beyond that before you start getting into any sort of problems. But on top of that, they're designed to take about half the load that they would see vertically in the sideways direction around the same time. And so really what looks like quite an event from an outside observer point of view is probably well within the design envelope of the landing gear and of the airplane.
When you design the landing gear you engineer, do you run it through all different types of crazy out there scenarios? This possibly could happen. There's a 1 in 1 million chance, but we're going to test for that?
Yeah, it's a mix of test and analysis, really. It's hard to test for every single event, but we do consider that lots of events by analysis. And, 1 in a million actually, from a commercial airplane point of view, 1 in a million isn't rare enough. And commercial airplanes are really designed for events that are at the kind of 1 in a billion occurrence level. If they're going to have a really nasty outcome, then 1 in a billion is about the maximum you could accept. So we do look at a lot of things that we certainly can't do a billion tests looking for the one outcome. So that's mostly done by analysis, looking systematically with a failure mode and effect analysis and a bunch of other tools. What can fail? What can go wrong? Is there enough redundancy there? What happens if this happens? Do you catch that? But for those sort of loading events, those extreme events, we do a lot of interesting things in terms of the landing gear is drop tested. So we do simulated landings on each landing gear as part of the certification. And for those, you go up to the limit load, that's at 10 foot per second at the maximum landing weight. You typically go beyond that up to about 12 feet per second. These are large commercial airplane numbers. If it's something that's going on a U.S. aircraft carrier, the numbers are much higher, for instance. And so we would have that collection of testing. And then there's static testing, limit and ultimate strength testing that happens. There's fatigue testing, where we simulate the entire life structurally of the landing gear. Generally, those tests take several years to run, and looking to see how they behave. And then a lot of individual equipment tests, looking at the performance of everything, looking at the environmental conditions. Does it operate properly when it's really hot? How about when it's really cold? Cover the whole wide range. Does it work when it's covered with ice, for instance? So all of those things get tested to prove that it's going to be reliable in service.
Weather is interesting. You can be in Alaska, it could be very cold, or you can be in Phoenix, Arizona, and it'd be 120 degrees in the middle of August. Is there temperatures that the aircraft can only land at a certain temperature because either the tire or the gear, is there temperature constraints on where a plane can and cannot land?
Yeah, well, I think once you've taken off, the plane can always land, regardless of the temperature. My flight instructor once told me, takeoffs are optional, landings are mandatory. And there's a lot to that, but we knew that was it last year, the year before, there were some pretty hot temperatures out in Arizona, and some flights were canceled because they were beyond the limits for the airplane. And the aircraft industry, the aerospace industry, is a very conservative industry, and we design for a wide range of events. We test for those. We do a lot of analysis for them. But if you're just a degree over the proven limits, people's natural conservatisms will come in, and so the airplane would probably have been entirely fine to fly in those situations. But generally, as an industry, we are very reluctant to take any risk at all. And so they would have kept the airplane on the ground. Practically, for something like a landing gear, high temperatures maybe not necessarily a huge issue. High ambient temperatures like that. Colder temperatures can be more of a problem. As you get down to the really cold temperatures, below minus 40, down to minus 50, minus 55, things like that. Rubbers get pretty hard. The compressed gas, which is inside the shock absorber, and the oil, which is inside the shock absorber, is contracted. It's not doing as much work as it would before. And so the cold temperatures are often harder to meet the performance requirements than the high temperatures.
You hit on a lot of interesting things around the landing gear. So your typical passenger, they look out the window. Oh, there's a landing gear, and they feel it on impact. But how does it work?
Well, I mean, really, there's a lot of things in the landing gear, but fundamentally, most of it's a big shock absorber. And unlike the shock absorber that's in your car, where often you've got a metal coil spring or some sort of metal spring that does the springing, and then you've got an oil damper. In the landing gear, we combine the spring and the damper together, and typically the spring is compressed gas, usually compressed nitrogen, and it's a type of damper which is known in other industries, but it's an oleopneumatic is the most commonly found type of shock absorber. And so you've got that shock absorber which is there to absorb the vertical landing energy as well as to damp out bump loads and things like that. And then you've got a bunch of structure around it which is designed to hold that to the airplane and allow it to pivot and rotate up into the bay so it can retract. The reason to retract the landing gear during flight is to reduce the drag and allow the airplane to go further and faster. And so you've got a lot of structural bits which are designed to fold up and allow it to retract, but then lock and hold it rigid in the extended position. At the bottom of the shock absorber, you've got an axle or several axles, which are going to hold the wheels, brakes, and tires. And then you've got all these systems which link all of those things together, put the brakes on, control the brakes, make sure that there's appropriate anti-skid braking, which is quite interesting in and of itself. And so those are the bunch of the bits that all work together. And then you've got indication systems that let the airplane and the pilots know the status, whether there's any issues, and how everything is working.
Anti-skid braking.
Yep.
You said interesting. I'm interested.
Sure.
What is it?
Well, we know most of our cars these days have anti-lock braking systems, which are designed to predominantly keep the wheels turning so that we can just stomp that brake pedal and we can keep steering. One company used to advertise it as stomp and steer, I think, was the the way to go. And those brake control systems in cars are pretty impressive these days as well. But on aircraft, the goal has been, because in general on aircraft we don't put brakes on the nose gear. There are always exceptions, but generally you have steering available. The purpose on aircraft ones is to really maximize the braking deceleration capability. And so the anti-lock braking systems which are used, the anti-skid braking systems which are used on aircraft, are seeking the maximum deceleration or seeking the maximum tire-to-ground friction that they can get. And they are constantly playing with the brake pressure to take it to a point of incipient skid of the tire and then backing off slightly and then finding that peak again. So they're always hunting for the best it can do, given the friction and grip that's available.
With all the parts in the landing gear, and you alluded to this earlier, what does your average landing gear weigh?
It's tough to give you just a number on that because there's really no average airplane, but maybe as a percentage is the way to look at it. So a typical landing gear system, so the complete set of landing gears, wheels, brakes, tires, all the valves and bits and pieces, probably runs at around the 3.5% of the all-up weight of the aircraft. So that would be the complete weight of the airplane, fuel, people on board, and everything like that. You sit at that sort of 3.5% range. Now that's, you can go lighter and you can go heavier. It depends on what type of airplane it is. If it's a special purpose airplane, we mentioned military cargo airplanes, they need to land on soft fields, so you're going to necessarily have more landing gears for that, so they're going to have a yet higher percentage. You can have some airplanes that are a little bit lower, but that's sort of roughly where it sits.
The 3.5% of the average weight of a plane goes into the landing gear. There's obviously the airlines, commercial airlines, I'm assuming same military, they want to make the aircraft lighter for a variety of reasons. Oh, yeah. As they look to make it lighter, how do the metals change on the landing gear?
Well, it's a good question. Historically, the real winning metal for landing gear has been ultra high tensile strength steel, steels that are up at the kind of 280 to 300 KSI ultimate tensile strength, so about as strong as you can get in a metallic material. And those have been the standby materials for many, many years. So one of the ways in the metallic world to go lighter is to move to some high-strength titanium materials. And we see a lot of airplanes out there over the past 20 years have put more and more titanium into the landing gear. Now, titanium, the titaniums that we're talking about here are very strong, but they're not as strong as steel. But their strength-to-weight ratio is much better than steel or aluminum. And so that's how they get on. But you need to have the space available to use them. If you are really volume constrained, then steel is still probably the best material to go for because it gives you the smallest part to do the job. But titaniums are a great way forward. But then looking out to the future, where are we, what's after titanium? Where are we going to? We could move away from metals into more composites, which is where some of the a lot of airframe structure has gone. Really, what's out there in sort of clear blue sky is maybe metal matrix composites, composite material where instead of being a plastic, it's the reinforcement is actually a metal, and but you have fiber reinforcements. Now they're always perennially tomorrow's material. Very tough to industrialize those.
Where does Safran's carbon brakes technology fit into that ecosystem?
It's a good question. So in the past, most brakes were metallic brakes. So in the friction brake, you need to store the heat in something. So you clamp those brakes on in your car. Typically got a brake rotor. Usually it's probably a cast iron of some sort. You've got some sintered friction materials that are pushing against it. Typically in cars, we've got one rotor at each corner. I've got an old car. It's got drums on the back, but basically the idea is, you've got something rotating. It's a chunk of cast iron, and you've got some frictional material that pushes against it, and the heat goes into the metal part. Now, in the landing gear world, light airplanes have brakes that are just like that. But as the airplanes get heavier and heavier, you need more and more energy, and you're trying to put more and more energy into a relatively small volume. And you also need to get a fairly high torque. And so what we look at doing there is we end up with multiple disc brakes. So you've got a stack of discs that turn and a stack of discs that don't turn, and you squeeze those together. And in the past, those were predominantly steel with sintered material. There was some time where beryllium was used as a material there, which was quite light, but beryllium has quite a bit of health hazards associated with it, so the industry has moved away from beryllium. But reinforced carbon is really the standout material to replace metallic brakes. And really, that's a real strength for Safran Landing Systems is in the development of that carbon material. That material, reinforced carbon was used for things like the space shuttle leading edges. It was originally a material developed for rocket engine, rocket nozzles, things like that. It's one of the few materials that has structural strength up at 2,000 degrees C, something like that. So it can be glowing, incandescent, and still has some strength. And so that the material there, it stores heat, but it also is a reasonable friction material. And so in a reinforced carbon brake, the rotating part and the static part are they're both the heat sink and the friction material itself, which gives an advantage. And on an airplane like a 737 or an A320 or something like that, to replace steel brakes with carbon brakes saves hundreds and hundreds of pounds at the aircraft level. It is a huge weight savings. And you see most modern commercial airplanes almost use carbon brakes exclusively because of that huge weight advantage.
The airlines that are going to operate the A320 or the 737, they'll save money, especially with rising jet fuel prices. And if you just look at the New York Harbor's trading at $732 a barrel, those tickets are going up. So if you can reduce weight, that's really a positive. So Safran's developing this really interesting, I frankly call it cool technology. So it's got me thinking, this type of metal, that type of metal. How do you put a plan in place to ensure the consistency in your supply chain? So if you're going to get metal, say, from vendor A, and you're going to get the carbon from vendor B, and then let's say B merges with C, how do you ensure consistency in that supply chain so the material that you're getting, is high quality and it'll be safe for your customers?
Yeah, it's a great question. And I think, one of the things we see in the aerospace industry in general is that there's a fair amount of standardization of materials. So a lot of materials are standardized by something like an AMS spec. And those include some quality performance aspects. Safran Landing Systems, we also have our own material specs, which may use something like the AMS as a baseline, but then we add on top of it our own needs, what we want from it, and that would give the technical requirements. But then one of the things that we do, and a good example is that ultra high tensile strength steel that is really the bread and butter of landing gears. That is a huge material for us. We buy from a number of different vendors. It can be made in a number of different ways, but we work with the supply chain to put quality control process into place, even to the point of looking at melt monitoring. So, rather than just checking that the material is okay when it arrives at our, on the back of a truck at our facilities, we've been involved right from the beginning of the melting of that material with our suppliers, make sure that the process that they're following meets what we're after. Also takes advantage of the learnings that we've had over the years about, what makes a good material, what do you need to control at certain points. And so the way we do it is through, of course, a number of rules that need to be followed, but really it's engagement with those suppliers, engagement with the partners to make sure that we are together putting together a great material and a consistent material.
It sounds like you have a great supply chain team.
Absolutely. And it's a global supply chain, right? This world is globally interconnected. We're bringing in material from all over the world, and then we're selling it onto airplanes that fly over all over the world. And and it's always a changing environment. So we've got a great team that goes out there and works with the suppliers, and we've got great suppliers and partners that are committed to providing high quality material in that area.
When you look at the global trends, there's a move towards electrification in the ground, but it's coming to aircraft. There's a large movement towards electrical aircraft. There's also hydrogen aircraft coming. As if you want to say alternative fuels and electrification come online, does the landing gear have to change?
It may very well need to change. It's possible, some of the alternative fuels, things like e-fuels and synthetic aviation fuel, are not going to change the airplane itself, although the infrastructure would change significantly. Something like hydrogen is going to significantly change the airplane because the volume of fuel that you need to have on board to do the job increases significantly. Even if the weight doesn't change or the weight is reduced with the hydrogen, the size of the tanks is quite large. And so we could see a change in the shape of the airplane, and then the landing gear would have to react to that change in the shape. Electrification is an interesting one because today on a larger airplane, you take off full of fuel and you land near empty, with some reserves. And so the takeoff weight and the landing weight are quite different, especially for a long-haul airplane. It's flying over oceans. An electric airplane is the same weight at landing that it is at takeoff. And so in a light airplanes today are designed to be the same weight at takeoff and landing anyways. But a medium haul or longer haul electric airplane may have a larger landing weight than it does, the equivalent one does today. And so that could have some impacts on the landing gear. Well, for me, all of those are very manageable. What I see is perhaps more interesting is say, well, what can the landing gear do that really enables a new airplane shape, that makes new fuel possible, that makes the airplane itself more efficient? And so we may well see a change in other trends because the fuel is one change, but also airplane shapes are becoming more efficient, wings are getting longer, and so that drives impacts as well. We talked about this crosswind landings. And imagine that the wings are even longer than they are today. The amount that the airplane can roll to come down a touch is going to be reduced. And so what can the landing gear do to enable that, to change that? Those are some of the things that we're thinking about, and we're trying to look at how can we help our customers, the aircraft manufacturers, come up with airplanes that are more efficient, that help everybody meet the environmental challenge and targets that we have.
The shapes are interesting. I'm just going to throw out an example that popped in my head. So you take your traditional 737 raised to 320. If you added on 3 to 6 feet on each side, it raises the question, do you have to rebuild the terminal because the planes are going to be wider or eliminate certain gates? That opens up a whole interesting conversation. Absolutely.
I think people will be reluctant to do things which have enormous infrastructure changes, and so we can take an example of something that Boeing's done on the 777X, which is a great new development of their 777 airplane, but it has a longer wingspan than the previous one. And what they've actually done is hinge the wingtips so that they fold up. So when the airplane lands, it lands, but as it's rolling down the runway after the wings aren't needed to generate the lift anymore, they actuate it and they fold up those wingtips, and then they can get into the same parking stand as the previous 777. So they get the longer wingspan, but don't have to change any of the airport infrastructure to support. So we could see that perhaps in a future generation of short and medium haul airplanes. That could be something that's done.
I like that approach because you said, because if you have to rebuild the nation's airports or globally, and they use the EU or Southeast Asia, yeah, that's a large infrastructure bill that we're not in a position to foot yet. So I really like that. And you mentioned sustainability. Sustainability is extremely, extremely important. How is Safran reducing its carbon footprint?
We've got a number of activities that are going on in that space. One thing is we are committed to getting aviation to be carbon neutral by 2050. That's in line with some global commitments. And really, when we look at that, there's a number of things that have to be done. For us, the biggest carbon emissions come from the use of our products. So effectively, the aviation fuel that's burned to carry our products around the sky. And so in order to reduce that fuel burn, it's things like, well, how can we enable the more efficient airplane? But also, how do we reduce the weight of the product, of the equipment? And so those are key areas. And about 75% of all of our research and technology development investment is going into environmental aspects like that. How do we reduce that fuel burn? How do we help make the transition for the industry? The other area, which as a percentage is nowhere near as big, but it's still a very important one, is how do we decarbonize? How do we reduce the carbon footprint of our factories, of our plants, of our day-to-day operations? And for that, we have some strong commitments to reduce the amount of natural gas that we are burning, to change the electricity. Now we are an international company with footprint all over the world, and so using electricity in one country is quite different, say, than in another. So in countries where electricity is predominantly coming from thermal fossil fuel sources, we're actively working at putting in systems that are move to solar, move away from those. Other areas we have far less carbon intensive electricity generation, and so we're focused there on other consumers like natural gas and other aspects. So a lot of activity in the business, both on the offices and the factories, but really focused on what can we do in the product to reduce its weight and to help airlines and aircraft manufacturers reduce fuel burn for the future.
Another industry that focuses on reducing weight is racing, car racing. Safran's learned a lot from car racing. What have you learned?
Well, I think we learned there is wow, the development time is fast compared to aviation. Yeah. So to come up with a new product in aviation, develop it from idea to it entering service with passengers on it is almost a decade. Whereas the cycle to put something out in Formula One is probably weeks in comparison. So it's really a lot of the lessons we pull are on that. How do we work quickly? How do we take good ideas and bring them in, evaluate them? We use it as an incubator for some of the material development. So where we're strongly involved in automotive racing is on the brakes and clutches, things which use our carbon material technology, and it allows us there to work with different things like what are some of the ceramic coatings that could go on that, a lot of coating development, and we can learn some interesting technical lessons there and then see how they filter into the aviation world.
There's a trend that's going on in the mobility world of learning a lot from aerospace. When did Safran say, okay, there's a lot we can learn in racing? When was that decision made?
We've been involved in racing for a long time. It's hard for me to give you a specific date on that because we've been involved in aviation since the founding of the business. But given Safran Landing Systems is itself formed really from three separate companies that had developed many years back, which was Messier, Dowty, and Bugatti. And so the Bugatti company, the car company today making the Veyron and other fantastic things, that company, the origins of it it's part of the DNA of Safran Landing Systems. And so there's been a deep involvement in car racing for many, many years. But more recently, we see that we've for a couple of decades had strong involvement in motor car racing with the carbon products and brakes and clutches.
There's a deep culture of awesome engineering happening at Safran, and I really like that. I want to zoom out for a moment because you're a pilot. You earned your pilot's license in high school. Is that how you first became interested in landing gear? Your work, you're doing the pre-flight inspection, going around. Was it aha? There's something here. I want to learn more. Is that how you went down this rabbit hole?
Perhaps, yeah. It's I've thought about this, and I'm not entirely sure I can really identify that moment where my romance with landing gear began. But I did drag my parents around to many air shows and museums as a kid, and I've really always had a love of aviation and airplanes. And maybe it's because the landing gear, what you can see when you're not as tall and you're standing there and you see that's the stuff that's at eye level. But I've always loved what I would say the wonderful complexity of landing gear. They're a beautiful piece of mechanical engineering, and they're solving a very interesting challenge, and that I've always liked that about them. There's something to me really appealing. The technical challenges which need to be solved with them are really quite interesting, and there's no single solution. There's a wide variety of landing gear, just as there's a wide variety of airplanes, and each airplane gets its own bespoke design with its own interesting challenges, and I think that's what's really quite alluring about it.
You took the early romance with landing gear. You got an incredible job, and then you said, "Oh, we're going to get married. I'm going to publish a book." So you published the SAE published your book, "The Design of Aircraft Landing Gear."
Yeah,
really well done, extremely comprehensive. Could you talk about the book, please?
Yeah, absolutely. Comprehensive, I guess, is the word for it. And I'd started off thinking, well, maybe I'll write a little pamphlet about landing gear, and 1,000 pages later, we've got the design of aircraft landing gear. And I think really I love books. I love to read, and I love landing gear. And this was a way of putting them all together. And the book itself, what I hope I've come up with there is something which is really aimed at two audiences. One is the people like myself who work in this industry, who are really interested in landing gear, but who wants a reference, want an idea book, leaf through it and see how other people have solved the problem. And the other one is people who are just learning. Maybe they're designing an aircraft, or they're in college and they're part of an aircraft design team, and the person who gets the task to design the landing gear, where do they turn? So there's a book where you can open it up and you can see what there is to do, work your way through it, and try to capture. You can't put all the world's knowledge in, and I certainly don't have all the world's knowledge. But what I hope is that it's a place that you can find a lot of great information and pointers to where you can find more. And just to try and grab as much information as possible and help people out in that way. Help them find a solution to their problem.
If you're listening to the podcast and you're interested, you can go to sae.org. And you can pick up a copy of The Design of Aircraft Landing Gear by Kyle. It's well worth a read. And he said if you're in college, you want to learn it, or you're like me and you're just generally curious, there's a lot of really great information there. And so, Kyle, putting this conversation into context, what is the future of landing gear?
Very good question. I think until we figure out anti-gravity paint, we're going to have landing gear on airplanes. And so really, we'll see a lot of trends of how do we reduce that weight. Weight that's the historical one we've tried to pull down over many years. But, can we get more weight out of it, get more capability out of it? Can we help airplanes enable something else? One of the things we try to do as landing gear engineers is to make the landing gear as simple and as robust and as reliable as possible. And simplicity is something that we push for because we say, reliability is complexity is the enemy of reliability. Really, and so the fewer parts that are there, the more reliable it's going to be. On the other hand, though, we may need to add a bit of complexity to a landing gear in order to enable new airplane functionality. And so there are times where adding capability to the landing gear gives an overall life cycle advantage to the airplane. And so that's it. We might see, for instance, if we look at the future, something like e-taxi, electrically driven wheels, are a way of reducing fuel burn on the ground. Looking at existing airplanes today, an e-taxi system could enable a 4% fuel burn reduction for some operators flying short-haul routes from congested airports, because it can shut the engines off and move around on our electrical power on the ground. We see that perhaps future airplanes may not have an onboard hydraulic system anymore. Today, most airplanes are using engine-driven hydraulic pumps to do their flight controls, and we use that for the landing gear. So we're preparing to be able to deliver all of the landing gear functions electrically, extension and retraction electrically, steering electrically. And so we're able to do that today if that meets the need of the future airplane. And we'll likely see material changes as we move. More and more composites are likely to come in. Landing gears take high loads, so the composites you generally need are quite thick compared to airframe structure. And so we have some interesting technologies that we can offer the world in there as well. So weight and reliability and capability for the airplane, those are the key things that we are pushing to improve.
You highlight a lot through this weight, and I can't wait for it to be lighter. It's better for the environment, it's better for the aircraft manufacturer, and it's better for the passenger. So well said on that, and your landing gear is awesome. And as we look to wrap up this insightful conversation, what would you like our listeners to take away with them?
Well, I guess the great thing is landing gear is an exciting thing. I love landing gear, but it's not just me. We've got lots of people who are really interested in this. The problems, there are still problems to be solved, and it's an exciting. Every day is an exciting thing to do to create new landing gears to support the ones that are out there. Safran Landing Systems is a fantastic place to work, and we're hiring. So we've got 700 roles available now that we need to fill this year. So come on out. We're looking for people to join us, and the Safran Group, the broader Safran Group, is a wonderful place with about 12,000 positions to be filled. And so come and join us as we continue on this journey and push to decarbonize aviation and find the future of aviation for us all.
Decarbonizing aviation is the future because today is tomorrow, tomorrow is today, and the future is lightweight landing gear. Kyle, thank you so much for coming on SAE Tomorrow Today.
Thank you very much. It's been great.
Thank you for listening to SAE Tomorrow Today. If you've enjoyed this episode and would like to hear more, please kindly rate, review, and let us know what topics you'd like for us to explore next. Be sure to join us next week when we speak with May Mobility's co-founder and CEO, Edwin Olson. Ed will share May's strong vision on how shared autonomous vehicles can complement existing transit and help everyday people get to where they need to go.
SAE International makes no representations as to the accuracy of the information presented in this podcast. The information and opinions are for general information only. SAE International does not endorse, approve, recommend, or certify any information, product, process, service, or organization presented or mentioned in this podcast.